States of a quantum system are said to be degenerate if they give the same value of the energy upon measurement. Today we'll explore the relationship between the symmetries of a particle in a 3D box and the degeneracy of its states. Consider the following problem. A particle of mass m moves in a three-dimensional box with edge lengths L1, L2, and L3. Find the states that correspond to the first 5 allowed energies if L1 equals L2 equals L and L3 equals 2L. Which of these states are degenerate? Remember that for a particle of mass m in a 1D box from x equals 0 to x equals L, the wave functions and energy levels are labeled by the quantum number n, which starts at 1 and goes up. Now, in 3D, the wave function is separable, which means Schrödinger's equation separates into independent equations for x, y, and z. The wave functions for the 3D box turn out to just be products of the 1D wave function, and the wave functions and energy levels are labeled by 3 quantum numbers, n1, n2, and n3, which are independent, and each start at 1 and go up. Okay, so before we discuss the states for our asymmetric box in this problem, let's remind ourselves of a key feature of the symmetric box, L1 equals L2 equals L3, and that's that some of the states with different quantum numbers n1, n2, and n3 give the same energy. They're degenerate. And this is because when you take out the L1 equals L2 equals L3, so this just becomes an L squared, then there's a symmetry in this energy of exchanging n1, n2, and n3. So for instance, when n1 equals n2 equals n3, the degeneracy for the symmetric box is, well, none. It's 0. So for instance, the ground state of the symmetric box, n1 equals n2 equals n3 equals 1. But for one of n1, n2, and n3 different from the other two, then the degeneracy is 3. So, and that's because states with just one different quantum number can be ordered as such. For instance, for the first excited level for the symmetric box, states 121, 211, and 112 all give the same energy, and so there's a threefold degeneracy of those states. While if all of n1, n2, and n3 are different, then there's a sixfold degeneracy for the symmetric box. And so that's like, for instance, the state psi 1, 2, 3. There are 5 more combinations of n1, n2, and n3 equals 1, 2, 3 that would all give the same energy. Okay, so we'll return to this table in a minute. For now, let's write the first 5 energy levels for our asymmetric box. So for the problem at hand, we have L1 equals L2 equals L, and L3 equals 2L, so the z direction is twice as long. And what I'm going to do is I'm going to rewrite the energy of the level n1, n2, n3 as E naught over 9 times 4 n1 plus squared plus 4 n2 squared plus n3 squared, where I've defined this constant E naught equals 9 pi squared h bar squared over 8 m L squared. And the reason I define this constant like this is because then the ground state, which corresponds to n1 equals n2 equals n3 equals 1, since that's the lowest value of the n's, indeed equals E naught. So the state psi 1, 1, 1, which has no degeneracy, has energy E naught. So then we can go on increasing N1, N2, and N3 and figure out what these energy levels are. I go through the details of this in the attached PDF. The main point is that since we've broken the symmetry between the x and y axes and the z-axis, this factor in front of N3 is different from the factor in front of N1 and N2. It's smaller. So for the next couple of levels, increasing N3 will give the next highest energy. So this level will give 4 over 3 E naught, if I plug in the numbers. And the second excited state, which also has no degeneracy, will give 17 over 9 E naught. And then at the point when I increase either N1 or N2, there's a twofold degeneracy because there's still a symmetry between exchanging N1 and N2 in this energy. So at this energy level, where we have psi 1, 2, 1, we also have psi 2, 1, 1. So there's a twofold degeneracy, and these both give the same energy of 7 over 3 E naught. And finally, our fifth energy level, so the fourth excited state, will actually turn out to be threefold degenerate, with quantum numbers 1, 1, 4, and then 1, 2, 2, and of course, since N1 and N2 are different, there's the exchange of them 2, 1, 2. So this will give 8 over 3 E naught. And this is our energy level diagram for this problem. Let's interpret these results. So just like the symmetric box, our asymmetric box has a symmetry of exchanging N1 and N2. The symmetry is also evident in the wave function. Here I've plotted the probability distributions for the two degenerate states at level 7 over 3 E naught, which are degenerate because of this symmetry of exchanging N1 and N2. And the symmetry between x and y is evident by the fact that these two plots of the probability distributions are mirror images of each other. So, of course, the important difference between the symmetric case and our case is that we've broken the symmetry between the z direction and the x and y directions. So this is evident by the fact that some of the degeneracy in the symmetric case gets lifted. When n1 equals n2 equals n3, well, we still have no degeneracy. For instance, that's the case for this ground state here. But when one of them is different, we now have two cases. When N3 is the different one, so that's, for instance, the case of this first excited state, there's no degeneracy because N3 does not have a symmetry of exchanging with N1 or N2. But when either N1 or N2 is the different one, then there's a twofold degeneracy of swapping N1 and N2. And that's, for instance, this 7 over 3 E naught case that we plotted the probability distributions for over here. And finally, when all three are different, then there's also a twofold degeneracy because there's only the degeneracy of swapping N1 and N2. So the main point is that breaking the symmetry between the z direction and the x and y directions lifted some of the degeneracy. This is a generic feature in quantum mechanics. The more symmetric the system, the more degeneracy.